moving on to number 6. Again, plot as many points as you can, and after I tried, I was really only able to graph these 3 because the other ones did not fall within the table or the graph that I had. So at first try, if we tried to connect the dots, we'd have this drastic curve, and using the table, we know that the curve is going to continue to go downwards very, very quickly actually. Notice how we have slight changes in x, but very drastic changes in y. So we're going to dive down, but towards the other side, as we change the x's, notice how the changes in the y's is very minimal, and it looks like we're getting closer and closer and closer to 2. So as we continue the left-handed side, maybe that left end behavior, if that sounds familiar, we're going to be getting closer and closer and closer to 2. So it looks like we have another exponential function. Notice how we have that horizontal asymptote, and we have that drastic change in the graph, whether it's going up or down. So we can classify this as we read it from left to right. Notice how the graph is going away from the asymptote. So this would be an example of an exponential growth. Since this is an exponential function, it's going to have the same properties that we discussed previously for number 5. Maybe we can go ahead and tackle domain and range. Moving left to right, domain would be all real numbers, and the range, like we said previously, is changing depending on the case, but for this particular example, we can go as low as we want, but we get closer and closer to 2 without ever reaching it. So there's our range. What I want to spend the most amount of time, though, with this particular example is talking about how we can figure out the equation for this m of x function. And since it's exponential, again, it normally has the form a times b to the x plus c. Since we know the horizontal asymptote is at 2 and not 0, it was moved up 2 points. So we can automatically fill in a plus 2 for the c. Now in the last example, again, I said we got pretty lucky because we were just doing guessing and checking. But notice how some of these numbers might be perhaps a little bit more difficult to work with. First of all, because they're negative. Second, because they start to get very large, and in decimals might be hard to work with as well. So we're going to go ahead and take a mathematical approach to this example instead of the guessing and checking like we did before. So the mathematical way is to pick easy points to work with. Again, we don't want to make it more difficult than it has to be. And I would say perhaps that these 2 points are fairly simple, easy numbers. Some are negative, but we're not going to let that get to us. Let's go ahead and perhaps choose this 0 point first. So we can substitute in -6 for the y value and 0 for the x value. And notice how that's pretty important, because any number raised to the 0 power is 1. So we're essentially left with a times 1, which is just a. And now we can solve for a. Looks like we get -8. So this number out front, that leading coefficient, is actually -8. Let's go ahead and rewrite the equation now that we have that piece of information. So all that's left for us to figure out is this b value, and we can do a similar process by utilizing a different point. So perhaps we'll plug in -2 for the output and -1 for the exponent. My bad, I didn't mean to put plus c out there, we mean plus 2. So let's go ahead and solve for b. We can subtract 2 over, which would give us with a -4. We can divide the 8 over, so that would leave us with a 1/2. Now, b to a negative exponent, hopefully we are familiar with our exponent properties. If you have a negative exponent, you can flip it to make it positive. So this would look like 1 over b. And in order for this fraction to equal this fraction, it looks like our b value has to be 2. So now that we know what a and b are, we can go ahead and write our formal equation for m of x. Kind of running out of room, but I'll go ahead and write it up here. Our a value was -8. our base value was 2 raised to the power of x, and our horizontal asymptote was located at +2.